In this section, we'll be examining the relationship between convolution and linear time invariant systems, and amongst other things, we'll be introduced to what is known as the impulse response of a system, and learn of its significance in the context of linear time invariant systems. In the preceding material, we were introduced to the mathematical operation known as convolution. At this point, I'd like to explain the significance of convolution, particularly in the context of linear time invariant systems. But before I can do this, I first need to introduce the notion of the impulse response of a system. So the impulse response of a system is simply the output that's produced by the system when the input is the delta function. So in mathematical terms, if we use script h to denote the system, and we use little h to denote the impulse response of the system, then this is the equation that defines the impulse response of a system. In other words, if we put delta into the system as input and observe what the output is, which is denoted by script h delta, this is by definition equal to the impulse response. Now, with the definition of impulse response in mind, I can now introduce the significance of convolution. So for any linear time invariant system with input x, output y, and impulse response h, a relationship of this form is satisfied. In other words, the output of the system y is equal to the input of the system x convolved with the impulse response of the system h. So in other words, an LTI system simply computes a convolution and nothing more. So this is why convolution is quite important when we're talking about linear time invariant systems. The impulse response also is very important, as you can see here, because the impulse response completely characterizes or describes a linear time invariant system. In other words, if we know h, we know everything about how the system behaves, because if we know h, we can always determine what the output will be for any given input by computing this convolution. When working with an LTI system, often one of the first things that we want to determine is the system's impulse response. Now, in practice, we can't really determine the impulse response of a system by direct measurement, because to measure the impulse response directly, we would need to present the delta function as input to the system and then measure the output. The difficulty with doing this is that we cannot generate a good approximation of the delta function, since the delta function is infinite at the origin. So in practice, we often determine the impulse response through indirect means instead of trying to measure it directly. At this point, I'd like to consider a couple of examples. The first of these examples is a proof of Theorem 4.5, where Theorem 4.5 is just a statement of the second bullet on this slide. So we're going to show this particular result here. In this example, we're going to prove the result of Theorem 4.5. In other words, we're going to show that if we're given an LTI system, which is denoted by the operator script h, that has the impulse response little h, that this system satisfies an equation of this form. In other words, the output of the system is equal to the input of the system convolved with the impulse response of the system. So to do this, what we're going to do is we're going to start with the left-hand side of this equation and then manipulate it into the form of the right-hand side. So starting from the left-hand side, we simply have this expression here. And the first thing we're going to do is we're going to use the fact that delta is the convolutional identity. And the way we're going to use this is we're going to take the x here on the left-hand side and rewrite it as x convolved with delta. Because delta is the convolutional identity, convolving any function with delta doesn't change anything, and we get back the function x. So this is a valid thing to do. The next thing we're going to do is we're going to take our star notation for convolution here, and we're going to rewrite it as a convolution integral. So going from this line to the next line, all we've done is we've just rewritten things in terms of an integral. Now at this point, what we're going to do is we're going to use the fact that the system h is both linear and time invariant. And first we're going to use the fact that the system is linear. So when we're applying the operator h, anything that's a constant as far as this operator is concerned can be pulled out of the operation performed by h because it's linear, and in particular because of the homogeneity part of linearity. And in this particular case, since tau is a constant with respect to the operation being performed by h, we can pull x of tau out of this operator h. So we can factor this out. We can also pull out the integral which appears here as well. So we're going to basically pull out both the integral and x of tau, this constant, with respect to the operation performed by h, to write this next line. So here all we've done is we pulled the integral and this x of tau outside of the operation that's being performed by h. So this is relying on the linearity property. In other words, it's relying on the fact that h is a linear system. Now what we'll do next is we're going to rely on the fact that the system is time invariant. And the way that this helps us is in the following way. If we look at this expression that I've underlined in green here and focus on what it's saying in more detail, effectively what we have is a delta function that's being shifted by tau. So we have a time shift being applied first. And then this result is having the operator h applied to it. So we have two operations happening, a time shift and h. Now because the system is time invariant, what this means is these two operations commute. So we can interchange their order and it won't change the overall effect of these two operations. So this is what we'll do next. We're going to interchange the order of the operation performed by h and the time shift that's being applied here and write them in the opposite order. So this green underlined quantity here is essentially those operations but reversed in order. So now what we have is we're first applying h to delta. So we're first applying h to the delta function, and then afterward we're applying a time shift by tau. So all we've done is interchange the order of the time shift and the operator h. And again, we can do this because the system by assumption is time invariant. The next thing that we can do is we can observe that by definition, h delta is simply the impulse response of the system. In other words, by definition, we have that this relationship here holds. Because by definition, the impulse response of the system, which is denoted by little h here, is the output that we get when we put delta into the system, which is exactly what this right-hand side represents. So we can take h delta here and we can replace it, with h, which gives us the next line. And at this point we can simply observe that the integral that we have on the right hand side here is simply x convolved with h. And this essentially completes the proof. Now we've shown that this quantity on the left hand side, which is this left hand quantity here, is equal to this right hand side quantity x convolved with h, which is this right hand side here. The next example that I'd like to consider is the example 4.5. In this example, we're given a linear time invariant system, which is denoted by script h, and we're told the system has the impulse response little h, which is equal to the unit step function, and then we're asked to show that this system is characterized by this particular equation here. Well, in order to do this problem, there's not really many approaches that we have based on what we've learned so far. One thing that we could use is the knowledge that because the system is LTI, we know that it must satisfy an equation of this form. In other words, the output of the system is always equal to the input of the system convolved with the impulse response of the system. So let's try using this and hope that we can show what we want to show in this problem based on this particular relationship. So just copying this equation to the line below, we have this line here. Now what we're going to do is we're going to substitute in the function that we're given for h. In this problem we're told the impulse response is the unit step function, so we can substitute u for h, which gives us the next line here. And now what we're going to do next is we're going to expand this star notation for convolution in terms of a convolution integral. And frequently we need to do this when we're solving problems. Often it's difficult to get any insight into what's going on mathematically when you have convolutions written as stars. Often you need to expand them out in terms of their definition, in other words using a convolution integral. So this is what we've done on the next line here. We've simply written out the convolution in terms of an integration. And what we'll do next is we're going to split this integral here into two sub-integrals. In other words, we're going to divide the range that we're integrating over here from minus infinity to plus infinity, in other words the whole real line, into two smaller pieces. One which goes from minus infinity to t, and the other which goes a little bit past t, in other words a little bit greater than t, up to infinity. And the reason for doing this is that we're going to split things in this way so that this unit step function factor, this u of t minus tau, in one integral it's going to always be equal to 1, and the other integral is always going to be equal to 0. This just helps us to simplify things more easily. In this particular case, in the first integral, this unit step function factor u of t minus tau is always equal to 1. The reason for this is because of the range that we're integrating over here, t minus tau, the quantity that corresponds to where we're evaluating the unit step function, this is always going to be a non-negative quantity. In other words, it's either greater or equal to 0. This is the place where the unit step function is equal to 1. So this is always going to be equal to 1, this underlying quantity here. Whereas in the second integral, in this case, the unit step function factor u of t minus tau is always equal to 0. The reason for this is due to the range that we're integrating over here. We're integrating such that tau is always slightly bigger than t up to positive infinity. Because of this, this quantity t minus tau will always be a strictly negative number. In other words, we're evaluating the unit step function at a negative point, which will correspond to the value 0. So because of this, this second integral just drops out. We're essentially integrating 0, which is 0, so this integral is gone. And what we're left with is just the first integral. And in this case, we can replace this unit step function factor by the constant 1, because it's always equal to 1 in this case, which gives us the last line here. And this completes what we're asked to show, because we're asked to show that this left-hand side here is equal to this right-hand side here. In other words, we're asked to show this result in equation 4.24 above, which we've shown is true now. Earlier we were introduced to the impulse response of a system. On this slide I need to introduce another type of system response known as the step response. So as the name suggests, the step response of a system is simply the output that's produced by the system when the input is the unit step function. So mathematically speaking, if we let h denote our system and let s denote the step response of the system, the step response is simply defined by this equation here. In other words, we're taking the input to be the unit step function, feeding this into the system h, and the output that's produced, which is denoted by hu, is what we define as being the step response of the system. Now it turns out that the impulse response and the step response of a system are related by this equation here. So h is the impulse response and s denotes the step response. So what you can see from this equation is the impulse response is simply given by the derivative of the step response. And this is important in a practical sense. As I mentioned earlier, often when we're dealing with linear time invariant systems, we want to know the impulse response of the system, because the impulse response completely characterizes or describes the system. However, we can't really directly measure the impulse response, because doing so would require us to generate a delta function as an input to the system, but the delta function is infinite at the origin, so we can't really generate either the delta function or even some reasonable approximation to the delta function. So we need to determine the impulse response using some indirect means. And one choice that we now have at our disposal is to use the step response. In other words, we could determine the impulse response of a system in the following manner. First, we directly measure the step response of the system. And unlike the impulse response, the step response is something that we can measure directly in practice, since it is possible to generate very accurate approximations of the unit step function. Then once we have the step response of the system, we can determine the impulse response simply by taking the derivative of the step response. Often block diagrams provide a very convenient way in which to represent systems. When drawing block diagrams that involve LTI systems, we often label the LTI systems with their impulse responses. The impulse response makes a particularly good label for an LTI system, since an LTI system is completely characterized by its impulse response. So for example, suppose that we have an LTI system with input x, output y, and impulse response h. We can denote this in block diagram form using the block diagram shown at the bottom of this slide, where h is denoting the impulse response of the system. Earlier in the course, we were introduced to two basic ways in which systems can be interconnected. In particular, we looked at series interconnections and parallel interconnections of systems. What I want to do on this slide is revisit these two types of interconnections, specifically in the context of LTI systems. So first I'm going to consider series interconnections. So suppose that I have two LTI systems. The first one has impulse response H1, and the second system has impulse response H2. And suppose that I connect them in series like what's shown in this diagram here. Now suppose that we consider the overall effect of these two systems, in other words the combined effect of both the system H1 and H2, and we view this as one bigger system with the input x and the output y. A question that we might ask is this combined system LTI? And it turns out that it is. And this leads to a second question, which is that given that the system is LTI, in other words the combined effect of H1 and H2 is a system that's LTI, what's the impulse response of this system? And this is what this second part of the figure over here is trying to show, is that if we connect two LTI systems in series with one another, their impulse responses convolve. In other words, the combined effect of these two systems together is they behave as a single LTI system where the impulse response is H1 convolved with H2. In other words, the individual impulse responses convolve with one another. So another way to look at this, what this equivalence is saying, is that when we connect LTI systems in series with one another, their impulse responses convolve. And then in the second half of this slide, I want to look at parallel interconnections of systems. So suppose we have two LTI systems, one with impulse response H1 and another with impulse response H2. And then we connect them in parallel using this type of configuration shown here. And suppose that we view this system, this combined parallel interconnected system here, as a single system with input X and output Y. We might ask the question, is this combined system LTI? And it turns out that the answer is yes. This system will be LTI overall. And then this begs the second question, which is, what is the impulse response of this LTI system? And it turns out that the impulse response of this system overall is simply the sum of H1 and H2. In other words, this system over here on the left behaves as if it's a single LTI system where the impulse response is H1 plus H2. So another way to look at what this equivalence is saying is when we connect LTI systems in parallel, their impulse responses add. At this point, I'd like to consider an example to further illustrate some of the concepts introduced on this slide. And in particular, I'd like to do example 4.7. In this example, we're given a system with input X, output Y, and impulse response H, as shown in the figure at the bottom. In other words, we have our system with input X on the left and output Y on the right. And we're told that the system consists of a number of LTI subsystems that are labeled with their impulse responses. So this block here is a LTI system with impulse response H1. This block here is another LTI system with impulse response H2. And lastly, this block here is another LTI system with impulse response H3. And what we're asked to do is to find the impulse response of this overall system. In other words, the system with input X and output Y. Now the way that I'm going to approach this is I'm going to divide this problem into two smaller problems. I'm going to first analyze the left side of this block diagram. In other words, I'm going to consider a system with input X and output V. In other words, the left side of the block diagram. And I'm going to consider a second system, which is the right side of this block diagram. In other words, a system with input V and output Y. And then at the end, I'm going to combine the results that I get for each of the left and right side of this block diagram to find my final answer. So before I proceed, the first thing I'm going to do is I'm going to label all the different signals that appear in this block diagram that aren't yet already labeled. And in order to do this, I'm going to use this important piece of knowledge off to the side here, which is that recall for any LTI system with input X, output Y, and impulse response H, it's always true that Y is equal to X convolved with H. In other words, for any LTI system, the output of the system is always the input to the system convolved with the impulse response of the system. And we're going to use this fact repeatedly in order to label the different signals in this block diagram. So the first signal that we can label is kind of trivial. We can label this signal here, this top input to the adder, because if we trace back in the block diagram here, this is simply connected to X. So very trivially, this top input to the adder is simply X. The left input to the adder, though, we want to label this particular signal. So what we do is we look at where this signal is coming from. It's coming from the output of this system H1, and the input to this system, which is an LTI system, is X if we trace back in the block diagram. So what we have here is an LTI system where the input is X and the impulse response is H1. And we know from this fact over to the side here that the output of such a system is just the input convolved with the impulse response. So this output here is going to be X, the input, convolved with the impulse response H1. So this is where this label X convolved with H1 comes from. And we can do a similar thing for this output here, the output of the system H2. Again, we have a system which is LTI. Its input, if we trace back in the block diagram, the input to the system H2 is this input X. So X is coming into the system, H2 is the impulse response. Because the system is an LTI system, the output is just X convolved with H2. In other words, the input convolved with the impulse response. So this is where this X convolved with H2 comes from. And then lastly, we can label the output of this overall system here And to do this, we simply observe that here we have an LTI system with impulse response H3. The input is V and the output is Y. And in particular, we're trying to find a label for Y here. So the output here is going to be equal to the input V convolved with the impulse response H3. So this is where this label here comes from, V convolved with H3. So with all these signals labeled, now we can proceed on to write some equations much more easily. So first I'm going to focus on the left side of this block diagram. So the first thing I can do is I can write an equation relating V, the output of the left side of the block diagram, to X. And what I can do for this is I can write V is equal to the output of this adder. So V is equal to X, this top adder input, plus X convolved with H1, which is this left adder input, plus X convolved with H2, which is this bottom adder input. In other words, I have this equation here. So this is just coming from the left side of the block diagram that I've labeled. And what I want to do is I want to write this equation that I have highlighted in the form that it looks something like V is X convolved with something. If I can write this equation in that form, then the something that's convolving the X must be the impulse response of the system. And for this purpose, it would be very convenient if all three of the terms that I have here on the right-hand side were all of the form X convolved with something. The later two terms are of this form. In other words, this term is X convolved with something. We have X convolved with H1. And this last term is also of that form. It's X convolved with something, where in this case the something is H2. But in the case of the first term, X is not convolved with anything. It's just X. But it'd be really nice if we could have this written in terms of a convolution. So the trick that we use here is we simply observe that delta is the convolutional identity. So we can take X and we can convolve it with delta, and this doesn't change anything. And the way that this helps us is now we can, all three of these terms here, the first, second, and third term, they all have the form of X convolved with something. So we can use the distributive property of convolution in reverse. It kind of looks a little bit like a factoring operation. And we can pull out this convolution by X from all the terms, and we can rewrite the right-hand side like this. So we've just used the distributive property in reverse. And now from this we can observe that the impulse response of the left side of the block diagram is simply the function that I've highlighted here, because now we have something that looks like V, which is the output of the left side of the block diagram, is equal to the input to the left side of the block diagram, convolved with something. This something must be the impulse response of the system. So we've sort of analyzed quite thoroughly the left side of the block diagram. Now let's move on to the right side of the block diagram. Well, the right side of the block diagram, just by inspection, we have that Y is equal to V convolved with H3, because both of these labels are labeling the same point in the block diagram. So this gives us this equation here. So this is just read off of our block diagram that we have labeled, which is just copied below. This is exactly the same equation copied below. And now what we're going to do is we're going to take the equation that we got for V, in other words for the left side of the block diagram. So we're going to take this formula for V here and substitute it in for V in this equation. And this gives us this next line here. And now what we want to do is we want to write this equation. On the left-hand side we have Y. Y is equal to X. And what we want to have is X convolved with something. And if we can write things in this form, Y is equal to X convolved with something, that something must be the impulse response of the system that we're dealing with. In other words, the system with input X and output Y. And this is what we're looking for in this problem. So with just some minor adjustments to this formula, in other words using some properties of convolution and so on, we can manipulate this right-hand side such that it has the form X convolved with something. And basically what we do here is we use the fact that convolution is both distributive and associative, and also we use the convolutional identity. Convolving with delta doesn't change anything. And the way that this helps us, first we can use the associativity property. We have two convolutions on this line. We have a convolution here and a convolution here. And the way that the brackets are written, we're first doing this convolution and then doing this second convolution afterwards. But we can interchange or regroup the convolution operations because this operation is associative, convolution is associative. So in other words, we can compute this convolution first. We can convolve the quantity delta plus H1 plus H2 with the function H3. And we can also, in the process of doing this, we can use the fact that convolving anything with delta just gives us the same function, which gives us this new expression on the right-hand side here. So we're basically using the distributive property to take this convolution again with H3 and distribute it across each of these three terms. And we're also using the fact that when we convolve delta with H3, This just gives us h3, which is our first term here. So this gives us this next line. And at this point now we can simply observe that we have an equation that has the form the output of the system, which is our system output y, in other words the output of this overall system, is equal to the input of the system, over here, convolved with this function here. But this function here must be the impulse response of the system. So this is what we're looking for. So essentially this is the impulse response, which is just copied on the line below here. So this is what we're being asked to find in this particular problem, the function h, which corresponds to the impulse response of this overall system. In other words, all these blocks combined, the system with input x, the output y, what is its impulse response? Well, it's given by this function here.